Hi there, I hope you're having a great day. Let me introduce myself first. I'm Anna, mobile development expert, passionate about quality software from Ukraine. I'm a Google developer expert in Dart and Flutter, and I recently became a Women Tech Makers ambassador. I have 8 years of experience in cross-platform mobile development, and I have been dealing with Flutter for work and leisure for over 3 years now. I currently work as a senior staff mobile engineer at a company called Tide. Tide is the leading provider of small and medium business accounts and is one of the fastest growing fintechs in the UK. We are transforming the business banking market, providing a smart current account that gives time back to business owners. I joined Tide about 8 months ago, and during this time we have been solving quite interesting technical challenges and developing some pretty exciting approaches to different parts of our mobile applications, which we create with the Flutter framework. And I'm here to talk about one particular topic, which is basic and advanced networking in Dart and Flutter, the way we implement it at Tide. Most applications, be it mobile, web, or desktop, depend on some kind of backend, right? Thus, an API layer is an integral part of application implementation. And I'm sure today you're going to discover something interesting for your particular Flutter project. I believe I should say it in the beginning. If you prefer written content, just recently I have published a series of 6 parts on the same topic. There you will find everything we'll cover today and even more. It has links to the GitHub repository containing the code we'll look into today. This talk will also consist of 6 parts. Parts 1 and 2 are dedicated to basic and advanced topics around data models with Freeze and JSON serializable. Parts 3 and 4 are about HTTP client and request interceptors with DO. And in parts 5 and 6, we'll talk about basic and advanced implementation of REST API requests with Retrofit. Each of these parts can be applied independently, but together they complement each other and form a full-fledged API layer implementation. Personally, I am most excited about the last part, where I'll show you how we hacked code generation to help us effectively implement hundreds of API calls. So be sure to watch till the end. For an example project, today we'll be developing a mobile application that displays a list of Marvel comics. Obviously, because we are talking about the networking layer of the application, we'll be downloading this list from Marvel Comic API. If you are going to run this application on your side, you will need to register and obtain your own API key. Here is a list of dependencies for today's project. We at Tide rely heavily on the code generating mechanism with BuildRunner. BuildRunner is a pub package that is added to the dev dependencies in pubspec YAML file. When combining it with packages providing builders, like for example Freeze, developers can only provide the configuration for what code to generate. And once this command is run, BuildRunner consumes those builders and the configuration and creates additional files in the file system, which contain Dart code that you would be writing on your own otherwise. The build argument stands for one-time execution. While developing, we are instead using watch for constant tracking of the configuration change and code regeneration. Okay, let's get started. I will be showing you a lot of code today, and maybe going too fast sometimes. Feel free to pause this video later and read the code more carefully, or refer to the GitHub repository. The link is in the article. In order to receive data from the backend, the first task is to create some data structures to contain this data, right? We will be receiving a list of Marvel comics, so let's work on a Marvel comic class. Here's how a plain Dart object may look like, right? Just a list of fields and a constructor accepting parameters. Looks okay, but it might be much better. The default implicit toString implementation will only print instance of Marvel comic. Implicit operator equals only compares object references and not their content. The images list is modifiable. There is no implicit copy with method. And if we were implementing it manually, this typical implementation would not allow updating nullable fields with null values. That's why we at type use freezed for every data class. Here is the same Marvel comic class declaration with freezed package. This is the configuration for the future generated code. Here we see a part file declaration, which provides a name of the file with freezed suffix, to which additional code will be generated. The freezed attribute above the class declaration, the factory constructor declaration, and the list of fields that the generated class will contain. Freezed also supports positional arguments, but we at type prefer named parameters. Non-nullable fields should be either required as ID field here, or contain the default value, like images list. We typically provide an empty list as the default value for list fields, so there is no need to check if a list is null when reading its values. Once the build runner command completes, there is a new Dart file generated. I'm going to show it in several pieces here. The new file is a part of the main Dart file with a class configuration. This generated class is an inheritor of the one we declared previously, and it contains the same list of fields. Just as in the declaration, the ID field is required, and all of the rest fields are nullable. The images list is given the default empty list value, and it is wrapped into an unmodifiable copy. The toString method is overwritten to give output in a human-readable way. The equals operator depends on fields values, performing a deep comparison of models and lists. And the same applies to the hashcode method. Also, because the generated implementation of a copy-with method gives all parameters a default value of freezed, it allows setting nullable class fields to null. Now that we have a Marvel comic data model implemented with freezed, it is time to teach the generator how to deserialize it from JSON. Actually, to make it serializable, all it takes is to add another part file and a special from JSON factory constructor. After these changes, freezed will ask JSON serializable to generate serialization logic to a new file with G suffix. Each field is serialized to and from map by the key, which is equal field name. Out of the box, JSON serializable can manipulate integers, doubles, strings, enums, lists, maps. Datetime gets automatically converted to and from string. The default value for an image field is used in case JSON doesn't contain any value. Looks good, but here is a problem. Let's say there is another data class, Marvel image. And now our Marvel comic contains fields of this type, thumbnail and images list. The generated code is somewhat unexpected. The toJSON method of the new Marvel image class is not called from the toJSON of the Marvel comic class. The fix can be to annotate Marvel comic class with the JSON serializable attribute with the explicit toJSON set to true. But we believe this should have been the default behavior for all classes. That's why we are configuring JSON serializable behavior for the entire project in a build YAML file, which holds the global configuration for all code generating packages. Now toJSON has changed. First, at the bottom, you can see thumbnail and images list are correctly serialized to JSON. And second, there is a new write-not-null method, which allows skipping null values when serializing Marvel comic to JSON. Now nullable fields, digital ID, title, modified, thumbnail, and format will be sent to backend only if their value is not null. Okay, now our models have a basic functional implementation of JSON serialization. Let's look into how this mechanism can be further customized. Every field can be annotated with a JSON key attribute, which controls how fields are serialized. Here, every field is given a name, format field is ignored, and thumbnail is given a different name. As a result, the generated code does not mention the format field, and the thumbnail is using that different name as a JSON map key. Even though most of the time JSON keys equal fields names, we prefer explicitly specifying key names for safe refactoring. The JSON key attribute also has the default value property, but when used, it only provides a fallback value for a field if it is absent in JSON and not when the plain constructor is used. Instead, we at Tide rely on the default attribute from the free package because it covers both cases, when a class is created via the plain constructor and when deserialized from JSON. Let me bring back the format field because next we are going to talk about enums. Here is the Marvel Comic format enum declaration. The generated JSON serialization logic declares a map and is using the exact enum item names as values. And here this map is used in from JSON and to JSON methods. In reality, for format field from Marvel Comic API, it uses human-readable values with spaces. So how to keep using code generation and configure enum names? We have to slightly adjust the enum declaration by adding JSON enum and JSON value attributes with the exact values as they come from the backend. Now the generated map is updated like this, and Marvel Comic is ready to properly parse format field from JSON that comes from Marvel Comic API. However, what if over time the API is extended with new comic formats? How to ensure the application remains stable without the necessity of an urgent update? First, we add an unknown item to each enum we obtain from the backend. Next, we provide it as the unknown enum value to a JSON key attribute and to the default attribute. Now the generated code changes to use Marvel Comic format unknown item in case JSON contains a new unknown value or null. This allowed us to make the format field non-nullable. We now have a Dart class Marvel Comic, which implementation is generated with Priest package and which can be serialized to and from JSON thanks to the implementation generated with JSON serializable. Cool, we now get into the advanced stuff. We saw earlier that types int, double, string, datetime, enums, lists, and maps are supported, and out of the box, datetime is converted to and from a string in ISO format. But what if for some reason the backend uses a different datetime format? Or if the data type in JSON does not match the one in the data class? For that, JSON serializable offers a converters mechanism. Let's now say that we are required to have string ID and accordingly a nullable string digital ID. Let's start with ID first. To satisfy this requirement, we'll create a JSON converter class called int-to-string-converter. This converter is designed to deserialize an int type field from JSON to a string type field in the Dart model. Here it is applied to ID field of now string type. As a result, int-to-string converter automatically gets applied in the generated file. Now, what about digital ID? It might seem logical that the same int-to-string converter can be applied to convert nullable int to nullable string. However, in Dart type system, nullable types are not the same as their non-nullable counterparts. Because of type mismatch, int to string converter simply would not be applied to digital ID in the generated file. Instead, we need another converter, nullable int to nullable string. Here it is applied to the digital ID field of now nullable string type. And it also gets used in the generated file. So far, converting string IDs to int IDs and vice versa, both nullable and non-nullable, is the only use case of converters for tight projects. Moving forward to a feature of Freest packages called unions. Marvel Comic API exposes a story summary object that describes a story in a Marvel comic. And stories can be of three types: cover, interior, and promo. In plain Dart classes, this record would look like this. And in Freest unions terms, it will be implemented like this. Here, a Marvel Story Summary class is a Freest model declared in the same way as the Marvel comic. The difference is Marvel Story Summary has three named constructors: cover, interior, and promo. The challenge is to keep using code generation with JSON serializable and automatically parse this type of complex data structure from JSON. The generated G file contains instructions on how to parse individual model types, and the generated Freest file contains a switch that decides what model type to parse based on the runtime type value. So, in order to properly parse Marvel Story Summary object to one of its union subtypes, the incoming JSON has to have a runtime type key with either cover, interior, or promo value. Obviously, it is unlikely that the backend would send such a property with exactly these values, especially the API we don't own. However, Marvel Comic API instead sends a type field that can be either cover, interior story, or promo. The Freest package provides ways to customize both the union type key with union key property and constructor names with Freest union value attribute. After these changes, the generated Freest file does switch on type field instead of runtime type, and now Marvel Story Summary class can be effortlessly parsed from JSON. But what if it's not that simple, or you need more control over what's happening during union parsing? Let's take a look at another example, the creator summary object. Marvel Comic API has all kinds of creator roles like editor, writer, inker, pencilier, colorist, and many more. So we have a new Freest union creator summary with named constructor for all creator roles we are interested in and other for all the rest. The API has two types of pencilier role, which we don't want to distinguish between, and want them all to be parsed as just pencilier. So how to solve this task? Once again, the generated Freest file contains a switch that decides into which union model type to parse. The trick is to modify the incoming JSON map, providing the required runtime type key with an appropriate value. So here, before passing the incoming JSON further to from JSON generated implementation, it is modified by append runtime type method. I have declared a map of correspondence between the role name coming from the API and the name of the Freest union constructor, which solves the double pencilier task. And other runtime type is provided in case the role name was not found in the map. Now Marvel's creator summary can also be properly parsed from the incoming JSON. Ready for the next union challenge? We looked at scenarios where a union type indicator is contained inside the union model itself, like the type field of a story summary or the role field of creator summary. But it's not the rare case when such an indicator is a part of the outer wrapping model. Let's take another example, Marvel Series Summary object. It has a format enum field, and depending on its value, the metadata union field should be parsed to different Marvel Series Summary metadata subtype classes. Essentially, the solution is the same. Somehow modify the incoming JSON to place a proper runtime type key. But this time I use the readValue method, which supports logic that requires accessing multiple fields at once. Here I provide the method name to the JSON key attribute, and here is what is going on inside. The incoming JSON map contains the data for the entire Marvel Series Summary object, not only a metadata field. This allows us to access both the value of the format and the JSON of metadata. First, I decode the format field from string to an enum, just as the generated code would do. Then I use the runtime types map below to pick the metadata union constructor name based on the format field. And then I put it inside metadata JSON map under runtime type key. And that's it. Using readValue feature does not change any of the subsequent decoding logic for the field. So read format metadata value method returns a JSON map dedicated to metadata. These were the three ways of parsing union types for the incoming JSON. Now to the last model-related topic. Oftentimes, backend responds with data wrapped into a generic response object containing request metadata, such as status code or timestamp. It is the right place to use generics for a data model that represents such a response object. This time, we are using JSON Serializable alone to create a generic Marvel API response class. Here, the FromJSON constructor accepts a second parameter, which informs how to parse the generic data field. The generated G file contains FromJSON implementation, which uses this parameter on data JSON value. Now, we can use this code to parse an API response containing Marvel Comic class. Okay, so far we have prepared a full-featured data model with default values, converters, enums, unions, and generic API response class that are going to be used later to parse and carry data obtained from Marvel Comic API. Next in our topics list is a DIO package, which provides an object to perform network requests. When created, the DIO object can accept base options that will be applied to every request, such as base URI, timeouts, query parameters, and headers. DIO object exposes get, post, put, patch, delete, and other methods. In here, if example API is given a DIO object configured as it was shown before, the GET request will be sent to the getExample path and will have two query parameters and two headers, one given here explicitly and one from the DIO base setup. Post and other methods can accept data to be sent with the request. We just saw how each DIO request can be complemented with headers or query parameters with static values. But what if, let's say, each request should contain a timestamp or another value unique for each request? As you can imagine, this logic will quickly be duplicated all over the project and may be forgotten about here and there. Instead, this should be implemented with an interceptor like this one. It overrides the onRequest and appends the required timestamp as query parameter to each request. It now has to be attached to the DO instance used to perform requests, and that's it. In fact, the Marvel Comic API imposes a more sophisticated requirement. Each request has to have 3 query parameters: public API key, timestamp, and an MD5 digest of the timestamp parameter, your private key, and your public key. Again, such a requirement can be easily satisfied with DO interceptor. To make the implementation closer to a real-life scenarios, the new interceptor accepts the public key as a parameter. The private key is asynchronously obtained from some service. After this interceptor is attached to the DO instance, all requests it makes to Marvel Comic API are authenticated. Creating an array of interceptor is intentional here. In tight projects, we typically use multiple interceptors for different purposes. By now, we have a configured DO object capable of performing authorized requests to Marvel Comic API, and a set of models to contain data. We are actually ready to perform a first API request. Here you can see the getComics method performs a GET request to comics bus. The obtained JSON data is of string dynamic map type. We use Marvel API response from JSON constructor. The comics API returns a paginated list of comic object, which on its own is a generic type. So we are using Marvel paginated list from JSON constructor inside response JSON parser. Now, because Marvel paginated list is also generic type, its from JSON also accepts 2 parameters. And we finally pass the Marvel comic from JSON there. As a result, getComics method returns a parsed Marvel API response object with a Marvel paginated list of Marvel comic models. We discovered what is DO and how to leverage its interceptors mechanism, and also made a first authorized request to the Marvel Comic API. Look at this repository, which uses Marvel Comic API we have just implemented. If we were to create solitary unit tests for it, it would look something like this. We'd mock Marvel Comic API and check that the repository returns the data from the API class. Solitary tests only test one class in isolation. Then we need to have tests for the API class and also tests for parsing logic. Instead, we test them all together via sociable tests that look similar to this. At Tide, we came up with another interesting application for the DO interceptors concept. Here I'm using all real implementations and am attaching a mock interceptor to a DO instance. This interceptor lets me mock the incoming JSON on the deepest networking layer with handler resolve call. This way, we can test JSON deserialization logic for all involved models with one test. There is an interesting side effect of this approach. Sometimes it may happen that the mobile application is being developed faster than the required API, or the backend dev environment may be down for maintenance. Or even trickier, we may have to develop an integration with a third-party service that is either being developed or can also be down for some reason over which we have no control. To unlock ourselves and keep developing the code as close to the production version as possible, we can use such DO interceptors outside of tests in order to mock a real API responses. So if I apply this interceptor to a production DO instance, it will not perform a real call to the Marvel Comic API to get comics list, but instead it will return a predefined response. This is a very flexible way to mock the backend behavior, including error scenarios. Now to another advanced networking topic, which is proxy support. There are multiple reasons the application should respect the device proxy configuration. Users might have a security setup configured on their device that prevents the application from using the internet at all if it doesn't respect proxy settings. The testing team might want to test the application against a mock backend, etc. By default, the device proxy settings are ignored by the application. Here's how we fix that. Internally, DO uses an HTTP client to perform requests through the adapter. The default HTTP client adapter exposes on HTTP client create callback, providing a chance to interact with the inner HTTP client object. It exposes a find proxy field that is a callback that reads the proxy settings. The find proxy function will be called with each request to DO object, and it is where the inner HTTP client can be informed of the current proxy setup. Currently, it returns direct, which means no proxy setup. Reading device proxy settings is an asynchronous process, but as you can see here, the find proxy call expects to be executed immediately. To overcome this limitation, we developed a three-part solution. First is a shared in-memory storage to hold and expose current device proxy settings. Second is a DO interceptor that asynchronously reads device proxy settings on each request and stores the result in that shared storage. And finally, a class that exposes a find proxy method that synchronously reads stored proxy settings and forms a proper response for the inner HTTP client. It is important that both interceptor and proxy finder share the same instance of proxy holder. When it all put together, the onRequest method of proxy interceptor is called before each API call and saves current device proxy settings in the proxy holder. The find proxy callback of proxy finder is also called before each API call, but after the interceptor, so it can be sure to read fresh proxy settings from the shared proxy holder instance. If there is no requirement to immediately catch the new proxy settings, proxy holder could return cached values until the app is restarted. Now we're done with the more advanced setup of the DO instance used to perform API requests. The rest of this talk is dedicated to the efficient implementation of REST API requests. The getExample method here consists of 4 lines of mostly boilerplate code, while the meaningful information is only the getExample path and the example response return type. We at Tide don't implement such calls manually, but instead use the retrofit package. Here is the new example API implementation. The REST API attribute annotates the entire example API class, which is now abstract. Factory constructor accepts a DO instance and returns a generated class constructor. The getExample method now only declares its return type and is annotated with get attribute providing a request path. The part declaration informs the file name for the generated code. Now, the generated class implements the abstract example API class declared before. In essence, the code is very similar to what was written in the manual implementation. The DO object injected in the constructor is requested for a string dynamic map via get request to the getExample path. The response is parsed to example response object via from JSON constructor. Here is another example with more attributes. The REST API attribute now accepts a base URL parameter. The post-example method is of type post, and its pass contains an ID, which is passed as a parameter to post-example method with pass attribute. The post-example method sends data of type string dynamic map, which is annotated with body attribute. The put example method is quite similar, but it performs a put request. It also accepts a pass parameter ID, but additionally has a query parameter named API key. Its body is of custom example body type. Finally, the delete example method only has a pass parameter ID and performs the delete request. The generated code reflects changes in the configuration file. Base URL, request types, pass, and query parameters were copied from the abstract example API class declaration to the generated implementation. Let's now apply this new knowledge to the Marvel Comic API we implemented previously manually. If you remember, the API returns data wrapped into a generic Marvel API response object containing request metadata. Retrofit covers this case as well. Look how the API implementation changed. We only declare the getComics method and annotate it with get attribute. The generated code is almost identical to the manual. Can you see the chain of from.json constructor calls for generic types? Retrofit has generated perfectly valid code for deserializing generics. Now we have re-implemented our Marvel API with only a few lines of code using Retrofit. Now I am going to talk all about request headers. Here is the first example. If a request is required to send a known set of static headers, it can be annotated with the headers attribute and specify a map of a header name and value. The generated G file declares a headers map with the same values and uses it in the request options. Now, if there is a need to specify these headers over and over again, here is the optimization trick. Dart allows using any constant as an annotation. Here we create a popular headers constant of type headers and use it instead of the actual headers annotation above the request declaration. This implementation is completely identical to the previous one, and it generates the same code. Now to another example, a single dynamic request header. Here, the header annotation is used in front of the method parameter. In the generated code, the header value is a method parameter, and it is put to the same headers map under header name key. The same trick with creating a reusable annotation is applicable to the header attribute. Here, the known header is saved to a const field popular header and used as an annotation. The generated code did not change after this modification. Next, to multiple dynamic headers. Here is again the headers annotation, but this time values in the map are dynamic. Check the generated code. The method accepts two parameters and uses them inside headers map under corresponding keys. Cool, huh? Extracting dynamic headers attributes to a const annotation is also possible. However, for it to work, the method parameter names should match values in the popular dynamic headers map. And that requirement is easy to forget if the annotation declaration is located in a different file. So far, we talked about individual request headers. If the same group of headers is required to be appended to all API requests, that can be done efficiently through DO interceptors. This interceptor here is pretty similar to the one responsible for making authenticated requests to the Marvel Comic API. It appends a static API key header, a timestamp calculatable header, different for each request, and an access key header obtained from the external source. When attached to DO instance, It sends this group of headers with each request. But let's say, for example, the login and forgot password requests do not require access key header. If there are only few requests that should not contain one of these headers, this interceptor still can be used with minor modifications. Obviously, developers have to remember to update the list of exceptions with each new request. This approach may work well for small to medium applications, but we at Tide use a more advanced technique. Are you still there? We finally got to the part which I personally am the most excited about. At Tide, we have a pretty extensive networking layer with hundreds of API calls. When developing apps at such scale, it is a must to minimize code duplication, optimize around creating only the code that matters, and decreasing the boilerplate as much as possible. So here is our challenge. Among other headers that are attached with each request, there are 5 particular headers that are sent with some or most API requests. They represent information available globally in the application, like access keys, some identifiers, information about installation, etc. But let's give them simpler names. All requests to our API require 2 to 4 of those headers attached. So for example, request A requires headers 1 and 2, request B, headers 2, 3, and 5, request C, headers 2, 3, 4, and 5, and request D requires only headers 2 and 4. Here, requests A, B, C, and D mean request types rather than some particular requests. Just imagine how providing these headers to individual requests with header attribute would look like. To use such API, developers would have to obtain the same information over and over again from the commonly available sources. Remembering that there are hundreds of requests such as A and B's in our project, it is hard to imagine the amount of code duplication this approach would lead to. Wouldn't it be cool to attach a DO interceptor that appends headers only to required requests? The challenge is to inform an interceptor about which requests require which headers. Ideally, such an interceptor should look similar to this. But what that some condition should be? Given our project scale, the approach with an exceptions list is not a feasible solution. We needed a way to mark each request with a set of headers it requires, which DO interceptor would be able to understand. I have to introduce you to a new attribute called extra, which is dedicated to holding custom fields. It allows providing an extra string object map to a request that can be later retrieved in DO interceptors. Here is the generated file where an extra map is formed and sent with request options. Now it can be read in DO interceptor like this. If request options contain the append header key and it's true, then add a header to options headers. We also clean up the extra map so no other interceptor processes the same data. Now back to the Tides request alphabet. Following this approach, we divided all API requests into groups based on the headers they require and created custom annotations for each group, request A type, request B type, etc. Now they can be applied over API requests. As a result, the generated file contains unwrapped extra map values. Now they can be read in DO interceptor to decide whether to append headers. And users of API are free from providing irrelevant from their point of view information and can focus on passing in only the data that matters. The created annotations can be applied over any retrofit request, including the Marvel Comic API we created previously. How cool is that? Okay, one last piece of information. Because our application allows managing members' bank accounts, Some operations are security sensitive and require users to enter their PIN or use biometrics so we can access some sensitive data. For simplicity, let's say we naively ask users if they agree to share secret data with a simple yes-no dialog. The obvious implementation is to call this method before calling each security-sensitive API request. However, such an approach has the same downside as we discussed before. Code duplication when implementing each security-sensitive request and taking care of irrelevant from the point of an API user information. The solution is also the same. Create a view interceptor and find a way to inform it which requests should be preceded by a user permission dialog. You might think, hold on, I know the solution. Use an extra annotation and append another marker to required requests. We also thought so, but it appears only one attribute of extra type is allowed on top of API request implementation. So we had to use another attribute that could annotate a retrofit request and have an effect on the generated code, which is the headers attribute. The advantage of using an extra attribute was that even if no interceptor is attached to the Duo instance and does not clean up the extra map, it's not harmful to have something in it because it's not really used when the request is sent to the backend. With headers, if no interceptor is listening for it and does not replace marking headers with something meaningful, it will be sent as is and may cause a misunderstanding with the backend. So we created a new annotation and a Duo interceptor that would wait for and process such a header. It detects if the headers map contains a header with a special value. If it does, the interceptor requests for secret data. If the request was successful, data is appended as a security header value and the request proceeds as normal. Otherwise, API request is rejected. And we remember to clean the irrelevant header value. Now this annotation can be used over an API request, which no longer accepts any parameter. And users of the API can forget about its implementation details. The created annotation can be used over any retrofit request. So here it is annotating the getComics request together with the previous one. Now each time user updates the list of comics, they are asked for confirmation. The same approach is applicable for post-request operations. It all depends on whether the code in the interceptor is executed before the parent on request call or after. So we now have looked into various ways of customizing API calls headers on a retrofit per request level, as well as globally in Duo interceptors. I have applied some really simple UI to display a list of Marvel comics we have been downloading today. So here is how it looks like. You can find all the code we saw today in the GitHub repository. The tools and approaches described in this series are very close to what we have created for Tide production code. If you find this approach as exciting as we do and would like to join our company to learn even more cool stuff we apply while developing our mobile applications with Flutter, check out our careers page for positions in different locations. We look forward to meeting like-minded, passionate professionals. Images and music used today belong to Marvel Entertainment, and these superheroes represent true sympathies of our engineering team. I hope you have learned something new and useful today, and you will be applying some of this stuff in your projects. Cheers!
Okay, now is the time for the questions section. So, welcome, Anna. I hope you are well.
Hi, thank you. I hope everyone enjoyed the presentation.
I hope to. So, another tips from Anna. She's a mentor at programs like Human Developer Academy and Road to GDE. She contributes to open source software and she also has an interest in mobile app design. Anna is a senior staff mobile engineer at Tide, and Tide is the leading provider of UK SME business accounts and one of the fastest growing fintechs in the UK. So we have the first question to her. In terms of code generations packages like Freest or similars, is there a good way to understand their impact on bundle size?
Good question. If you take a closer look, for example, Freest, JSON serializable, Retrofit, basically all code generating packages that I mentioned today are dev dependencies, which means themselves they are not included in the application, but the code they produce is. And this code you would be either writing manually or using code generating packages. When you do it manually, maybe you will do it slightly more efficient with less code, but honestly, it wouldn't be such a dramatic change to deny yourself the leverages of code generation.
Okay, thank you, Anna. The next question is, I am a web developer, but I am willing to make a native mobile app, and I am not sure how efficient is Flutter, and should I learn a new language like Dart to use it? Thanks.
Okay, I understand the concern about learning a new language, but honestly, if you saw any programming language, Dart would look somewhat familiar to you. I remember myself switching from Xamarin and C# background is what it was kind of obvious how to use it. And in terms of Flutter efficiency, come on, it's Flutter Global Summit. Of course, we're here all fans of Flutter framework and can talk about its benefits. It's efficient in the development experience, like you create beautiful mobile applications really fast, and it's also efficient in the production, meaning how fluent and nice the UI is you build with Flutter.
Okay, the next one is, what if some API needs timestamp in request and some API don't require? Then how to use Interceptor?
I believe this question popped up somewhere around parts 3 and 4. So I believe I have pretty much answered it in the parts 5 and 6. So go check it out.
Thank you, Anna. If retrofit is generating the JSON and also the Freest, isn't it duplicated or somehow it's just one the JSON generated?
To be more precise, Retrofit only generates the usage of toJSON method, not the implementation itself. So Retrofit doesn't even know from where that toJSON implementation comes from, whether you created it manually or it was JSON serializable who did the work. Retrofit just relies for the models to have this toJSON method. And if it receives a model which it expects should have toJSON method, but the model doesn't have it, actually Retrofit will complain in the terminal when you run this code generation command.
Okay, the next one, can you briefly discuss you use DO package instead of the building Dart HTTP package?
Well, the reason for that was pretty pragmatical. Like, it's what Retrofit is using. Like, the Retrofit generates code relying on the fact that you will be using DO as your HTTP client, and we are perfectly fine with it. We didn't find some downsides of using DO. And it died. with the scale of the products we create, we just really heavily rely on code generation, and it is a must for us.
Thank you, Anna. The last question we have, is it okay from architectural point of view to use repos in interceptors?
That is a good question. Probably one of those controversial philosophical questions we can have about architecture. As you saw in the examples I showed, I use constructor dependency injection most of the time. I left dependency injection mechanism out of the scope of the code I showed you, but actually that is the way we develop. So we expect dependencies to be injected. And as long as this separation is always kept in mind, I think it's fine. To be honest, at Tide, we also have an interesting testing strategy. So we test multiple layers together through widget tests. So for our tests, this kind of separation doesn't even matter.
Okay, we have a new question. How to make our plugin that support work with Build Runner?
That is on its own a very interesting and big topic. I remember there was a talk about it at Flutter Vikings on February. So I would probably advise you to go check it there, because a couple of minutes is not enough to explain everything. But it's definitely possible, and would be cool to see more useful packages for code generation.
Okay, thank you, Anna. Another one. Is it good idea to use injectable plugin for maintaining singleton and repos?
That is exactly the plugin we are using. So for dependency injection mechanism, we use getit and injectable, which registers all the dependencies for us in that getit instance.
Okay, this is the last question. Well, guys, if you have anyone, you can reach Anna through her social media links. We will share them to you. Thank you very much, Anna, for your presentation.
Thank you. Have a great day.
You too. Bye-bye.